March 29, 1974. A small NASA spacecraft called Mariner 10 hurtles past a tiny, cratered world just 327 kilometers above its surface, the first human-made object ever to visit the planet Mercury. As its instruments sweep across the barren landscape below, something strange shows up in the data. A faint signature. A whisper of gas where there should be almost nothing at all. Sodium. Around a planet that, by every reasonable expectation, should have no atmosphere whatsoever. Nobody on the Mariner 10 team knew it that day. But they had just stumbled onto a mystery that would take the better part of the next 50 years. 3 separate spacecraft missions and laboratory experiments recreating conditions 91 million kilometers away to finally solve. Today, we know the answer, and it's a stranger, more violent, and more beautiful story than anyone expected in 1974. This is the story of why Mercury is quietly leaking itself into space, one atom at a time. To understand why this discovery matters, we have to go back, way back, to a time long before spacecraft, long before telescopes, to a time when Mercury was little more than a strange, fast-moving point of light in the twilight sky. Ancient civilizations knew Mercury existed long before they understood what it was. The Sumerians recorded it in cuneiform tablets more than 4,000 years ago, associating the swift, moving object with their god Nabu, the divine scribe and messenger. Babylonian astronomers tracked its movements, meticulously across centuries of careful observation, building some of the earliest known astronomical records in human history around this elusive little world. The Greeks, fascinatingly, believed for a long time that Mercury was actually 2 separate objects. Because it never strays far from the sun, Mercury appears only in the hours just after sunset, or just before sunrise. Never in the dead of night, never high overhead. Ancient sky watchers, seeing it in the evening sky, called it Hermes. Seeing what appeared to be the same point of light in the morning sky, they called it Apollo. It took generations of careful observation before astronomers realized these 2 different objects always appeared on opposite sides of the sun, at complementary times of year, and were, in fact, the very same planet. Eventually, the Greeks settled on the name Hermes, the swift messenger god, quick and elusive, a fitting choice. And since Mercury is the fastest planet in the solar system, completing a full orbit around the sun in just 88 days, when the Romans absorbed and adapted Greek astronomy, they renamed the planet Mercury after their own equivalent messenger god, equally quick, equally hard to pin down. The name has stuck for roughly 2,000 years. For most of human history, that swiftness was also Mercury's curse, astronomically speaking. Because it orbits so close to the sun, Mercury never rises high in a dark sky, the way Venus, Mars, or Jupiter do. It's only ever visible for a brief window, low on the horizon, often lost in the glow of twilight. Even Nicholas Copernicus, the man who correctly placed the sun at the center of the solar system, reportedly complained near the end of his life that he had never once managed to get a clear, satisfying view of Mercury with his own eyes. It wasn't until the era of space exploration that humanity finally got a proper look. That brings us back to March of 1974 and Mariner 10, the first spacecraft ever to visit Mercury. Over 3 flybys in 1974 and 1975, Mariner 10 photographed roughly 45% of the planet's surface, revealing a world that looked eerily like our own moon, heavily cratered, ancient, and apparently dead. But Mariner 10 also carried instruments capable of detecting extremely faint traces of gas, and it was here that the mission delivered its biggest surprise. Around this small, airless, geologically ancient world, there was something. Not a real atmosphere. Nothing remotely like Earth's or even Mars's. But a genuine, detectable haze of sodium atoms, along with hints of other elements, surrounding the planet like a ghost of an atmosphere that had no business existing. This shouldn't have been possible. Mercury's gravity is weak, only about 38% of Earth's. Its surface temperature swings from over 430 degrees Celsius during the day to nearly minus 180 at night, among the most extreme temperature ranges of any planet in the solar system. And for a long time, scientists assumed Mercury had no meaningful magnetic field to protect it from the sun's relentless onslaught of radiation and charged particles. Given all of that, any atmosphere made of heavy elements like sodium and potassium should have been boiled off, blown away, or lost to space eons ago. So where was it coming from? And more puzzlingly, why did it persist, seemingly forever, rather than simply vanishing? That question would take half a century to fully answer. Before going further, it's worth being precise about exactly what we're talking about, because calling this an atmosphere is more generous than it deserves. Scientists use a more accurate term, an exosphere. An exosphere is the thinnest possible kind of atmosphere that can technically be called an atmosphere at all, so thin that the individual particles within it almost never collide with one another. In a real atmosphere like Earth's, gas molecules are packed closely enough that they constantly bump into each other, mixing and behaving collectively, the way air moves as wind or forms weather systems. In an exosphere, there is no such collective behavior. Each atom travels alone, launched from the surface by some external force, arcing upward along its own private trajectory like an individual cannonball, before either falling back down to the surface somewhere else, or gaining enough speed to escape the planet's gravity entirely and drift off into space. Mercury's exosphere is a genuine chemical cocktail. Spacecraft observations over the decades have detected hydrogen, helium, oxygen, sodium, potassium, calcium, magnesium, and even trace amounts of manganese, all hovering in this incredibly thin, ever-shifting halo around the planet. Some of these elements are relatively easy to explain. Hydrogen and helium are light and abundant throughout the solar system, and much of what's found around Mercury simply comes from the solar wind, the constant outward stream of charged particles blasting from the sun, some of which gets temporarily captured by Mercury's weak but genuinely real magnetic field. But sodium, potassium, calcium, and magnesium are an entirely different story. These are heavy metal atoms, in the literal chemical sense, alkali metals and alkaline earth metals. Under normal circumstances, they shouldn't be floating freely as individual atoms above a planet's surface at all. Here on Earth, sodium exists locked away inside salt crystals, inside rock, inside seawater, bound tightly within chemical compounds, never drifting loose into the sky on its own. For sodium or calcium or magnesium to appear as a thin gas hovering above Mercury, something has to be physically ripping those individual atoms out of the solid rock and minerals that make up the planet's crust and flinging them upward into space. For decades, planetary scientists proposed 4 separate competing explanations for how this might be happening. The frustrating part of the puzzle was that all 4 explanations seemed genuinely plausible on paper, and for a very long time, nobody had the data necessary to confirm which ones were actually correct, or in what proportion each one contributed. Let's walk through all 4, one at a time, because understanding these 4 suspects is essential to understanding the final, complete answer. The idea here is fairly intuitive. Mercury's dayside surface gets brutally hot enough, in theory, that some more volatile elements could simply evaporate directly off exposed rock, the way water evaporates from a sun-baked sidewalk on a summer afternoon, except here we're talking about far higher temperatures and metallic elements instead of water. A more technical name for a fairly elegant mechanism. Sunlight itself carries energy. Individual photons striking the surface can, under the right conditions, deliver enough of a jolt to knock an individual atom loose from the top layer of dust and rock, sending it flying upward. Picture sunlight acting almost like a tiny, invisible hammer, tapping atoms free from the surface one by one, all day, every day, across the entire sunlit hemisphere of the planet. They can physically knock other atoms loose on impact through sheer kinetic force, not unlike a cue ball violently breaking apart a tightly racked set of billiard balls, scattering them in every direction. Mercury has essentially no thick atmosphere capable of burning up incoming debris the way Earth's does. As a result, the planet is under constant, relentless bombardment by tiny particles of interplanetary dust and micrometeorites, many no larger than a grain of sand, but traveling at blistering speeds of tens of kilometers per second. Each individual impact instantly vaporizes a tiny patch of surface material on contact, releasing a small puff of atoms directly into the exosphere above. The trouble scientists faced for decades was that all 4 of these processes were almost certainly happening simultaneously, in varying amounts, in different regions of the planet, at different times of day, and under different space weather conditions. Untangling exactly which process was responsible for releasing which specific elements, and precisely when and where required a level of detailed, sustained, close-up observation that a handful of brief flyby images from the 1970s could never hope to provide. The real breakthrough began on March 18, 2011. When NASA's Messenger spacecraft slipped into orbit around Mercury, becoming the very first probe in history to actually orbit the planet rather than simply flying past it and moving on. Over the following 4 years, Messenger circled Mercury more than 4,000 times, mapping its surface in extraordinary detail and, crucially for our story, continuously monitoring the behavior of its exosphere across every stage of the planet's orbit. What Messenger revealed was that Mercury's exosphere is not uniform and it is not static. It is dynamic, constantly shifting, constantly responding, behaving differently depending on Mercury's position along its orbit, the time of day on the surface below, and even in direct response to space weather events unfolding on the Sun itself, 91 million kilometers away. One of the most striking early discoveries was that sodium in Mercury's exosphere is not spread evenly across the planet. Instead, it tends to concentrate heavily near the poles, forming distinct bright patches that Messenger's instruments could actually image directly, almost like faint auroral glows. This was an enormously important clue. If sodium atoms were simply boiling directly off the surface due to heat, as the thermal vaporization theory would predict, scientists would expect the highest concentrations near the blazing hot equator, not clustered around the comparatively cooler poles. Clearly, something else had to be driving this distinctive pattern. Messenger also confirmed something genuinely surprising. Mercury does have a real magnetic field, weak though it may be, roughly 1% the strength of Earth's. This magnetic field generates a magnetosphere, a protective bubble that deflects a portion of the incoming solar wind away from the surface, functioning in a similar way to how Earth's much stronger magnetic field shields us, just far less effectively, given how brutally close Mercury sits to the Sun. Here's the crucial twist, though. Because Mercury's magnetic field is notably weaker and offset from the planet's actual center, the incoming solar wind doesn't get deflected evenly across the globe. Instead, it gets funneled down toward the surface with particular intensity at the poles and in specific patches near the equator, through what scientists call cusp region S, essentially gaps in the magnetic shielding where solar wind particles pour directly down onto the surface below. Suddenly, the polar concentration of sodium made complete sense. The very regions where the solar wind manages to punch through Mercury's weak, lopsided magnetic shielding and directly bombard the exposed surface are exactly the regions experiencing the most intense sputtering, meaning the greatest number of metal atoms getting physically knocked loose through raw particle impact. But Messenger's data also revealed that this solar wind story couldn't be the entire explanation either. During certain intense solar events, coronal mass ejections, powerful solar flares, sudden violent surges in solar wind intensity, scientists observed dramatic, rapid spikes in Mercury's exosphere, with sodium concentrations sometimes doubling or tripling within just a matter of hours. This provided strong, direct confirmation that solar wind sputtering was indeed a real and highly significant contributor to the exosphere. And yet, on quieter days, when the solar wind settled down to calmer, more typical levels, sodium concentrations in the exosphere never dropped anywhere close to zero. Something else, entirely independent of the solar wind, was clearly still replenishing the exosphere, day after day, even in the complete absence of a strong solar wind driving the process. This is where more recent research, drawing on years of accumulated messenger data, combined with careful laboratory simulations back on Earth, and eventually reinforced by new observations from the joint European-Japanese BepiColombo mission, which arrived at Mercury in late 2025, finally allowed scientists to assemble the complete picture. Researchers gradually came to realize that the true answer was never going to be a single mechanism triumphing over the other three. Instead, the real answer was that different mechanisms dominate in different places at different times, and critically, interact with Mercury's surface chemistry in ways that nobody had fully appreciated until detailed mineral mapping data became available. Here is the key insight that finally tied everything together. Mercury's surface is not made of uniform, generic rock. Spectrometer data from Messenger revealed that different regions of the planet have meaningfully different mineral compositions. Some areas notably richer in sodium-bearing minerals, others richer in differ. Empty compounds entirely, reflecting billions of years of complex volcanic and geological history. Laboratory experiments conducted back on Earth, in which researchers blasted rock samples with simulated micrometeorite impacts and simulated solar wind particles under carefully controlled conditions, demonstrated that the efficiency of releasing sodium, calcium, or magnesium from rock depends heavily on precisely which minerals are present, and how those elements are structured and bound at a microscopic, crystalline level. Micrometeorite impacts turned out to be especially critical for releasing calcium and magnesium specifically. These heavier elements are far more tightly bound within Mercury's silicate rock structure than sodium or potassium, and it genuinely takes the sheer, concentrated violence of a physical impact, instant live vaporizing solid rock on contact, to liberate them efficiently and send them into the exosphere. Sodium and potassium, by contrast, being lighter atoms and more loosely bound within certain common mineral structures, are far more easily released by the comparatively tall, constant process of photon-stimulated desorption, where ordinary sunlight alone provides just enough energy to knock them free, as well as by solar wind sputtering whenever particles do successfully make it through to the surface. This distinction helped resolve a puzzle that had genuinely bothered scientists for years. Calcium in Mercury's exosphere displayed a strange recurring pattern, appearing to spike dramatically and predictably during specific periods when Mercury happened to be passing through streams of debris left behind by comets, essentially experiencing meteor showers, much like the ones Earth experiences. XEPT happening around Mercury instead. Researchers eventually traced this pattern directly to the debris stream associated with comet Encke, demonstrating conclusively that Mercury periodically plows straight through a trail of ancient cometary dust scattered across its orbital path, and that each time it does, the resulting hail of microimpacts produces a measurable, temporary, and highly predictable surge in calcium atoms detected in the exosphere. So the complete modern answer to why Mercury is leaking metal atoms is not one single elegant process, but rather a layered, constantly interacting system of at least 4 distinct mechanisms working together. Photon-stimulated desorption provides a steady, reliable, low-level background release of sodium and potassium across the entire sunlit day side of the planet, driven simply by ordinary sunlight striking exposed surface material every single day without fail, regardless of solar activity. Micrometeorite bombardment provides a constant background contribution across all detected elements, but emerges as the dominant, most efficient source, specifically for heavier elements, leaky calcium and magnesium, and produces dramatic, predictable spikes during Mercury's regular encounters with cometary debris streams, such as the one associated with comet Encke. Thermal effects play a smaller, more supporting role in the overall system, particularly influencing how quickly atoms redistribute themselves once airborne, since Mercury's extreme day night temperature swing significantly affects how individual atoms bounce, temporarily stick, and eventually re-release from the surface as the planet slowly rotates beneath the unforgiving glare of the sun. In other words, Mercury is not leaking metal atoms for one simple, isolated reason. It is leaking metal atoms because it exists in an environment of truly constant bombardment, from raw sunlight, from the ever-present solar wind, and from streams of ancient space debris, and its varied surface chemistry responds differently to each distinct kind of assault, releasing different elements through different physical processes, all happening simultaneously, all the time, across the entire planet. At this point, you might reasonably be wondering, fine, this is a genuinely fascinating chemistry and physics puzzle, but why should anyone outside a fairly small circle of planetary scientists actually care about the details of how Mercury loses trace amounts of sodium? Here is why this discovery genuinely matters, well beyond Mercury itself. Mercury belongs to a broad category of worlds scientists refer to as airless bodies, a category that includes our own moon, many of the larger asteroids scattered throughout the solar system, and countless moons orbiting the outer planets, from Jupiter's ice-covered Europa to Saturn's cratered Rhea. Every single one of these worlds shares the same fundamental challenge that Mercury faces, essentially no meaningful atmosphere to speak of, constant direct exposure to the solar wind and micrometeorite bombardment, and exposed surfaces made of raw rock, dust, or ice with nothing standing between them and the harsh space environment. Understanding, in precise detail, exactly how Mercury simultaneously loses and continuously regenerates its thin exosphere gives scientists an invaluable working model, essentially a natural laboratory, for understanding surface-atmosphere interactions across dozens of other airless worlds that are far more difficult, expensive, or currently impossible to study up close. This research also matters for something surprisingly close to home. Our own moon possesses its own extremely faint exosphere, and for years, scientists genuinely debated exactly how much of it originates from solar wind sputtering versus micrometeorite impacts versus other competing processes. The newly refined multi-process understanding developed through decades of Mercury research is now being actively applied to reinterpret older lunar exosphere data, collected by previous missions, and is directly informing the design of new instruments intended for future moon missions, including NASA's ongoing Artemis program, which aims to place detailed, sensitive exosphere monitoring instruments on the lunar surface for the first time in the modern era of space exploration. There is also a deeper, almost philosophical dimension buried within this discovery. Mercury's surface is very slowly, continuously eroding, not through wind or rain, since the planet genuinely has neither, but through this relentless, atom-by-atom, stripping process, driven directly by the very same sun that Mercury orbits so intimately close to. Every single day, without pause, sunlight, solar wind particles, and drifting cosmic dust are gradually, invisibly sandblasting Mercury's surface at the atomic level, flinging trace amoe, entities of the planet itself outward into space, where the overwhelming majority of those individual atoms are lost forever, and only a small fraction settle briefly into the faint, comet-like tail that Mercury quietly drags along behind it as it races around the sun. Mercury has been undergoing this slow transformation for well over 4 billion years, since the earliest days of the solar system. It will almost certainly continue doing so for billions of years still. Come, a slow, silent, continuous transformation, entirely invisible to the unaided human eye, only recently made visible to us at all through spacecraft instruments sensitive enough to detect the faint glow of individual atoms scattered by sunlight, all the way from 91 million kilometers away. The story is far from finished. BepiColombo, the ambitious joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, is continuing to gather fresh data as it settles into its final dedicated science orbit around Mercury. Unlike Messenger, which rel-eyed on a single orbiter, BepiColombo carries two entirely separate spacecraft working in tandem, each equipped with complementary scientific instruments, allowing researchers to study Mercury's exosphere and its surrounding magnetic environment simultaneously from two distinct vantage points at once, a capability that was simply never possible during any previous mission to the planet. Early data returned from BepiColombo is already helping to refine this picture even further, delivering more precise measurements of exactly how much sodium, calcium, and magnesium departs the surface under a wide range of diffee. Fearing solar conditions and helping scientists construct increasingly accurate predictive models capable of forecasting, almost like a genuine space weather report, how Mercury's faint drifting tail of escaping metal atoms is likely to change from week to week, depending directly on real-time solar activity. Scientists are also hopeful that these ongoing findings will eventually help illuminate Mercury's deep geological past, because different minerals release their constituent elements through distinct, entirely different processes and at different rates. The precise chemical composition of Mercury's exosphere can function almost like a rolling fingerprint of the planet's underlying surface geology over time, potentially helping researchers eventually map out where sodium-rich or calcium-rich rock formations are concentrated across regions of Mercury that spacecraft cameras still haven't been able to observe in truly high resolution. So the next time you happen to glimpse Mercury, a small, steady point of light hanging low on the horizon, not long after sunset, easy to miss if you're not specifically looking for it, remember that this small, unassuming little planet is, at that very moment, quietly leaking itself into the vacuum of space, one atom at a time, sand blasted continuously by raw sunlight, battered periodically by gusts of solar wind, and peppered on a predictable schedule by streams of ancient dust, in a slow and elegant process that took humanity fully 50 years of dedicated spacecraft exploration, from that first Mariner 10 flyby in March of 1974 to the ongoing work of BepiColombo today, to finally properly understand. And right now, at this very moment, trillions upon trillions of individual sodium atoms are streaming continuously off Mercury's surface, forming a faint, invisible tail stretching for millions of kilometers behind the planet as it races around the sun. A comet's tail trailing behind a world that is most certainly not a comet, and one of the strangest, most delicate, and most beautiful side effects of simply existing this close to a star.